Here's our problem for today. It's a problem from a category called related rates. We have a spherical balloon that's being filled at a constant rate of 100 cubic centimeters per minute. At what rate is the radius of the balloon increasing when the radius is 5 centimeters, and then later on when the radius is 12 centimeters? So the category of problem we have here is going to combine applications of the derivative, or interpreting the derivative as a rate of change, and the chain rule. Related rates means we're going to be talking about related derivatives. As the volume of the balloon increases, the radius of the balloon is also increasing. The balloon is getting bigger. But those rates will be related, but they won't be the same. They don't even have the same units. The volume is changing in cubic centimeters per minute. The radius will be changing in just centimeters per minute. So we're measuring them differently. But they are related. As the radius gets bigger, the volume will get bigger. Or as in this problem, as the volume is getting bigger, the radius will have to get bigger because we're maintaining a sphere. So let's write down what we know about the volume of a sphere. So we know that the volume of a sphere is 4/3 pi r cubed. So there's the equation for the volume of a sphere. Let's look at the rates that we have. A spherical balloon is being filled at a constant rate of 100 cubic centimeters per minute. So this 100 cubic centimeters per minute, that is how the volume is changing with respect to time. So this 100 cubic centimeters per minute is the rate of change of the volume with respect to time. The change in volume with respect to time. What we're looking for is the radius of the balloon is increasing. So the rate that we're looking for here's where we find the question. At what rate is the radius changing? So this says that we're looking for dr dt. Find how the rate of change of the radius with respect to time. These are two things that are related, the volume and the radius. We know how they're related. The volume is 4/3 pi times the cube of the radius. We know that dv dt is 100 cubic centimeters per minute. And we want to know how what dr dt is at particular values of r. So going back to our earlier question, we take the derivative and we plug in values, and that'll give us the rate of change at particular times or at particular points. So when the radius is 5 centimeters, so find dr dt when r is equal to 5, and later on when r is equal to 12. So we got two separate problems. We're going to plug in the 5, and then we're going to plug in the 12. All right. We're talking about rates of change. I see dv dt and dr dt. We're going to have to take some derivatives. What we have, though, is that the volume of a sphere is 4/3 pi r cubed. So if we take the derivative, all we have is the derivative with respect to r. So if I write if I take the derivative of 4/3 pi r cubed, if I find the derivative, by taking the, just doing the power rule. 3 times 4/3 is 4. Pi is a constant, r squared. That's the derivative of v with respect to r. So 4 pi r squared is the derivative of v with respect to r. That's not one of the rates that we're given. The rate that we're given is dv dt, the rate of change of the volume with respect to time. The rate of change that we're looking for is the rate of change of radius with respect to time. So just writing 4 pi r squared is only going to give us the rate of change of v with respect to r. But what we're looking for is dv dt. Or what we have is the rate of change with respect to time. So we use the chain rule. dv dt is dv dr times dr dt. dv dt is dv dr times dr dt, just using the chain rule. So the function that we have, 4/3 pi r cubed, we can find the derivative, but that's the derivative with respect to r. What we want is the derivative with respect to time. But now with the chain rule, I can write 4 pi r squared, that's dv dr, and just multiply by dr dt, the rate of change of r with respect to t, which in this case is what we're looking for. Now we just need to plug in the information and solve for dr dt. So dv dt is 100. This is equal to 4 pi times the radius. We're interested to find dr dt when the radius is 5 centimeters. So I'll put 5. Oops. And we're looking for dr dt. So 5 squared is 25 times 4 is 100. They cancel. So dr dt is equal to 1 over pi. And this will be in centimeters per minute. And this is when r is equal to 5 centimeters. I don't remember the reciprocal of pi. .318. So air is flowing into the balloon at a constant rate, 100 cubic centimeters per minute. When the balloon is 5 centimeters, when the radius of the balloon is 5 centimeters, the radius is increasing by 0.318 centimeters per minute. So that's how the radius is increasing when the radius is 5 centimeters. Later on, the radius will be up to 12 centimeters. So we'll just calculate again. We'll do the same calculation. We'll say 100. That's dv dt is equal to 4 pi, this time times 12 squared, still times dr dt. This is at a later time. This is at a later time. because the volume has increased to the point where the radius is now 12 centimeters. But we could just still solve for dr dt. So dr dt is going to be 100, 12 squared is 144 times 4, and then we'll divide by 100 by that. So let's see, 100 divided by 4 pi times 12 squared. So 0.055 centimeters per minute when the radius is 12 centimeters. This makes sense because we're putting the air into the balloon at a constant rate. Early on, the radius should be expanding quickly. Later on, when the volume is bigger, it's still going in at the same rate. So there's going to be less change in, the 100 represents less change in volume. In the beginning, 100 cubic centimeters per minute is lots of change. It's coming in fast. But when the balloon is bigger, then the radius is going to be growing at a lower rate because 100 cubic centimeters per minute is not such a big deal. Note that when the radius is 5 centimeters, the volume is 4/3 pi times 5 cubed. So 4/3 times pi times 5 cubed is 523, well, I'll just call it 524 cubic centimeters. So in 1 minute, the rate is going pretty, 100 cubic centimeters per minute is a big deal for a sphere with a radius of 5. But the radius at 12, or when the radius is 12, the volume is going to be much higher. So I'll replace the 5 with a 12. 7,238. When the radius is small, only 5 centimeters, the volume is only 500 cubic centimeters. So 100 cubic centimeters per minute is a big deal. But when the volume when the radius is up to 12 centimeters, the volume is up to 7,000 cubic centimeters. So 100 is not such a big deal. If you're arguing over $100 for a cheap Craigslist car that they're asking $524 for, $100 is a big deal. If you're like, I'll give it to me for $424, that's a huge hit in the sale price of the car. But if a car is being sold for $7,200, asking $7,100 is not such a big deal. It's less of a change. Any questions?
Yeah, Professor Lich, on the right, on the top right, we have 100 equal 4 pi, 5 points squared, dr dt. How do you get to 1/pi? Could you?
The 5 squared is 25. 25 times 4 is 100. So I just divided the hundreds out. And then I'm divide by 100.
How you get the pi on the bottom?
Because I'm trying to solve for dr dt. So I got pi times dr dt is equal to 1. So to solve for dr dt, I divide by pi.
And then you move the pi over. Got it.
Yeah, because if 1 is equal to 5x, then x is equal to 1/5.
My one other question, the one on the right, I think you set the sphere, V sphere to derivative, correct? And then you get the radius. Am I correct?
I'm sorry, I missed your question.
Oh, okay, the one on the right, we have 100 equal 4 pi. So basically, we set that to the first derivative, correct? From the sphere, from the V.
Yeah, so yeah, the dv/dt is the 100. 4 pi r squared is dv/dr. Right. And then the dr/dt is what we're looking for.
Once we get the radius and then we plug back to the volume sphere, the V sphere.
No. No, wait, are you asking what we were doing down here?
Yes, when we get the radius and then we plug back the V sphere with the formula, we plug the R back to the...
Okay, so this is not part of the problem. This is, so the problem specifically was to find the dr/dt when radius is 5 centimeters. That was the problem. What I'm doing now is explaining why the dr/dt was 0.3 when the radius was 5, but dr/dt is all the way down to 0.05 when the radius is 12. See that the radius is increasing at a much lower rate when the volume is very large, because the volume is so much larger.
Got it. I see it. Thanks, Professor Lich.
So I just wanted to emphasize, I wanted to discuss why there was such a big change in dr/dt when the radius went from 5 to 12.
Right. So the radius get bigger, the volume get bigger, larger.
Yeah.
Got it. Thanks, Professor Lich. I see it now.
And so the point is that when the radius is 5 centimeters, it's increasing much faster because 100 cubic centimeters per minute is a big deal for a 524 cubic centimeter sphere. But when the radius is 12 centimeters, we're at 0.06 centimeters per minute. The radius is increasing at a much slower rate because the volume is coming into the sphere at the same rate, 100 cubic centimeters per minute. And that's just not as noticeable when the volume of the sphere is all the way up at 7,200 cubic centimeters. So 100 cubic centimeters per minute is a big deal for 524. 100 cubic centimeters
Got it. Thanks, Professor Lich.
per minute is a big deal for a 524 cubic centimeter sphere. Let's say a bigger deal for 5 than it is for a 7,238 cubic centimeter sphere. So that was the point I was trying to make here. The related rates part of the problem ended here when we just calculated the rates, the dr/dt. What we want to get out of this is not so much calculate dr/dt. What we want to get out of this is to know that in this case, the volume is increasing and that's going to cause the radius to increase. And we want to understand how that relationship is going to work. And as the radius increases, because the volume is so much bigger, we should expect the dr/dt to get smaller because we know that the balloon is expanding really rapidly at the beginning, but it starts to slow because we're putting in the same amount of volume every minute, but that's not going to change the volume as much when the radius is large. So,
Professor?
Yeah.
Can you explain again how you got 4 pi r squared times dr/dt?
Yeah, I took the derivative. I have the volume of the sphere is 4/3 pi r cubed. So I took the derivative of that. But we're just being careful with the language. So 4/3 pi r cubed, the derivative is going to be 4/3 pi times 3r squared. Then the 3's canceled. But that derivative is that's the derivative of v with respect to r. And that's not what we want. We don't want the change in volume with respect to the radius. We want the change in volume with respect to time. So I didn't want dV/dr, I want dV/dt. The chain rule says dV/dt will be dV/dr times dr/dt. So that's us using the chain rule. So we're just using the chain rule. The 4 pi r squared came from our derivative rules. Multiplying by dr/dt is because we're doing the chain rule. Any other questions? Okay. So here's another type of related rates problem. So let's suppose that 2 cars are headed towards an intersection. Let's suppose that car A is driving east towards an intersection at 50 miles per hour. At the same time, car B is driving south towards the intersection at, let's say, 60 miles per hour. Let's suppose that car A is 4 miles from the intersection. Car B is 3 miles from the intersection. I forgot I was going to do the ladder problem next, but that's okay. We'll just continue on with this. So what's happening is as car A is going to the intersection and car B is headed towards the intersection, the cars are getting closer together. I set it up so that the cars would not crash at the intersection because I didn't put a stop sign there because I just didn't want to draw one. So fortunately, car B is going to go through the intersection before car A will get there. car B is going faster and it's closer. So don't worry about the cars crashing into each other. So there's what's happening is that the distance between the two cars is also decreasing. So if I call that R, we could ask, at what rate is the distance between the cars decreasing? So car A is driving towards the intersection, car B is driving towards the intersection, and I want to know at what rate is the distance between the cars decreasing at this time, or increasing if it happens to be increasing. So I've got a relationship between the values X, Y, and R, and I know what those rates are with respect to time. So I know that X squared plus Y squared is equal to R squared. And I know some rates in this problem. A is approaching the intersection at 50 miles per hour. So X is decreasing at a rate of 50 miles per hour. In terms of the variables in this problem, we would say that dx dt is equal to negative 50, because X is decreasing by 50 miles every hour. So dx dt is equal to negative 50 miles per hour. Similarly, dy dt is going to be negative 60 miles per hour, because the distance from car B to the intersection is getting smaller. So it'll be decreasing. So dy, I forgot what that sentence was headed. So both those rates are negative because the cars are driving towards the intersection. What we want to know is dr dt. These three rates are all related. Even if B was stopped in place and A was driving on a perpendicular road at 50 miles per hour, car A would be getting closer to car B, but it wouldn't be getting closer at 50 miles per hour because the distance between A and B is not on the same line as as X. If car B was parked at the intersection, then we would just say the distance between them is changing at 50 miles per hour, as if they'd be on the same line. But what's happening is that B is shrinking at a different rate than A is shrinking. So dr dt is shrinking in kind of this weird way. But we know how they're related. Since x squared plus y squared is equal to r squared, we can figure out how dx dt, dy dt, and dr dt are all related. What we're going to do is take the derivative of this equation with respect to time. So I want the derivative of this expression with respect to time. So the derivative of x squared is 2x But that's the derivative with respect to x. The chain rule says I have to multiply the derivative with respect to x by the derivative of x with respect to t. So the chain rule says 2x is the derivative with respect to x, multiply by the derivative of x with respect to t. In the next term, I take the derivative with respect to t. The derivative of 2y with respect to t is, the derivative of y squared is 2y, but that's the derivative with respect to y. And we have to multiply that by the derivative with respect to t. The derivative of y with respect to t. And over on the other side, the same thing happens. The derivative of r squared is 2r. That's the derivative with respect to r. So we have to multiply by the derivative of r with respect to t. Just using the chain rule all the way through. Now we have all these values. We know we want to know what's going on when car A is 4 miles from the intersection. So when x is equal to 4. When car B is 3 miles from the intersection, that means y is equal to 3. We can use that to figure out what's going on with r. Since x squared plus y squared is equal to r squared, I'll have 4 squared plus 3 squared is equal to r squared. And so that'll tell us that r is equal to 5. So when x is 4, dx dt is negative 50, y is 3, dy dt is negative 60, r is 5, dr dt is what we're looking for. So I have x, which is 4, times dx dt, which is negative 50, plus 3 times negative 60 is equal to 5 times dr dt, which is what we're looking for. I divided everything out by 2. I had a nice 2, so I just divided everything by 2. So I need 4 50s and 3 60s, divide that all by 5. So the cars are heading towards each other at 76 miles per hour. Or the distance, they're not heading towards each other. The distance between the cars is decreasing by 76 miles per hour.
Can I see what you did with the calculator again?
Yep.
The calculation.
I just took the 4 times negative 50 plus 3 times negative 60 and then divided it by 5 because I was looking for the dr dt.
Oh, okay.
Any other questions?
Yes, Professor Lynch. How you get that 4 multiply negative 50 plus 3? Could you?
X is 4. In the setup of the problem, I want to know dr dt when x is equal to 4. So x is equal to 4. The dx dt is how x is changing. That's negative 50 miles per hour. That's the dx dt is negative 50.
Mm-hmm.
Y is 3 because this is all happening when y is equal to 3 miles. So there's y equals 3. Y equals 3.
Right.
dy dt is the negative 60 miles per hour.
Okay.
There's dy dt is equal to r. I had to calculate r based on x and y. Right. And we figured out r is equal to 5. So there's 5, and dr dt is what we're looking for.
My one question, when we get to the very last, what is that number for? Yes, that's 76 miles per hour.
That's what we were looking for. That's how fast the distance between the cars is decreasing.
Decreasing. When we look at the graph right here. For the B, we have dy dt negative 60 miles per hour. On the dx dt, we have negative 50. How can we tell that's a negative? Could it be positive?
When the derivative is negative, a function is decreasing. When the derivative is positive, a function is decreasing. Since the car is driving towards the intersection, x has to be getting smaller. So the x is decreasing because the car is driving towards the intersection.
Oh, so when I see negative 50 miles per hour, not by looking the radius, right? Don't look at that, correct?
Yeah, we're just trying to figure out what dx dt is. And the reason we're saying that dx dt is negative is that x is decreasing.
For example, if it's plus 50 miles per hour, could it be like that? No.
If dx dt was plus 50 miles per hour, that means that x is increasing and the car is going in the opposite direction.
Okay.
That would be driving, the distance between the car and the intersection would be increasing.
Okay, thanks, Professor Leach. Thank you, got it.
All right, I'm going to post some problems from the related rates section. You're going to be given a function, and you're going to want to take the derivative of that function, but it's not going to be the derivative with the variable that you want. Just like in the first problem, you're given that the volume is a function of the radius, but I don't want dv dr, we wanted dv dt. So one of the styles of problems you'll get a function in terms of a variable that you don't want. You'll have dv dr, but you will want dv dt, so you will need to use the chain rule. And that's the big idea with this related rates. It's about understanding what the derivative represents, understanding the derivative as a rate of change, and putting that together with the chain rule. That's what's going on in related rates. All right, so we'll put off tomorrow. We'll do the ladder sliding down a wall problem. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.